Hola a todos, mi nombre es José y este video va a ser un poco distinto. Lo que quiero hacer es compartir con ustedes una charla que yo di mientras estuve trabajando en la Universidad de Valencia, en España. Y el tema de la charla es el modelo Polynomial Affine Gravity, que este es un modelo puramente afín de gravitación y es básicamente el modelo en el que he estado trabajando estos casi últimos 10 años, ¿ya? Entonces, cualquier duda o pregunta que tengan respecto a este modelo me la hacen saber en los comentarios y los dejo con la charla.
José Perdiguero Garde is going to talk about cosmological solutions in polynomial affine gravity. So, when you want. This is just for the audio or for I can use? Okay. Keep in your pocket. Okay. Thank you. Okay. Thank you so much for the opportunity to share with you my work related to polynomial affine gravity. And let's just go straight to the point. Okay, so what is polynomial affine gravity? Well, it is an alternative gravitational model where the gravitational interactions are mediated exclusively by the affine connection and not the metric tensor. Okay? And also, when we build the action for this model, we only use the irreducible fields of the affine connection, and the metric tensor does not play any role at all in its formulation. So in that sense, this is a purely affine model of gravity. And I just want to emphasize that the metric tensor does not play any role at all when we build this model. Okay? So how do we build a model? Well, to build a model, we need something like a building block. And our building blocks, we get those from the affine connection. And what we do is that we take the affine connection and we separate it into the symmetric and antisymmetric part. The symmetric part, which is the first term, allow us to define the covariant derivative, whereas the antisymmetric part is related to the torsion tensor. And the torsion tensor, we decompose it into its irreducible fields, which are the A and B field. The B field stands for the traceless part, and the A field, it is the vectorial part of the torsion tensor. Okay? And also, we want to preserve the invariance under diffeomorphism, which is why the symmetric part of the affine connection goes to the action indirectly through the covariant derivative. And as I said earlier, we do not want to use the metric tensor at all when we build this model, which is why the volume element that we use here, it is defined only by the wedge product. Okay, so our building blocks will be the A and B field coming from the antisymmetric part of the affine connection, the covariant derivative coming from the symmetric part of the affine connection, and the volume form, which is defined completely by the wedge product. So now that we have the building blocks, how we actually build the action? Well, what we do is something like a dimensional analysis technique. And what we do is that we define two operators, the N and the W operator. The N1 counts the number of free index. So in our convention, it is a +1 for every upper index, and it is a -1 for every lower index. So when we apply these operators to our irreducible fields, we get this expression, and the W operator counts the weight of the object. Okay, so the only object that has a weight, it is the volume element, the volume form. Okay, so we have the building blocks, and we have these two operators. An arbitrary term is defined by m times the A field, n times the B field, P times the covariant derivative, and Q times the volume form. Okay, so if we apply these two operators to this general term, arbitrary term, we get this result. And because we want to build scalar densities, we need to impose the constraints that Q must be equal to 1. And because these are scalar densities, the number of free index of the object must be equal to 0. Okay? So what we do is that we replace q equal to 1, then move the 4 to the left-hand side and multiply everything by -1. And what we get, it is a constraint equation. And this constraint equation tells us all possible, well, all the solutions to the constraint equation tell us all the possible terms that can go to the action, okay? So basically what we have here are 15 different branches of terms that can go to the action. But also we need to keep in mind that this is the structure of the term. So every term can have at least, maybe at least like 5 or 6 permutations, because what we need to do is to build every single possible contraction, and also we need to keep in mind the symmetries of the object. Okay, so what we do is that we take these 15 branches and study all possible permutations, and once we do that, we get the action. And the action, it is this one. So this is the action of the polynomial affine gravity in 4 dimensions, and it has 20 terms. And there are some nice features about it. Okay, so first of all, it preserves the invariance under diffeomorphisms just by construction. And also, it has this property that we call rigidity. And what I mean by that is that because we have this, because of the absence of the metric tensor in our formulation, we have a finite number of terms that can go to the action, okay? And this is not something that usually happens in metric affine theories. So because of the lack of a metric tensor, we have a finite number of terms that can go to the action. Additionally, the coupling constants are all dimensionless, which suggests, and this is speculative, that there is some sort of conformal invariance, and also it is power content renormalizable, which is a necessary condition, but not a sufficient condition to say that this model it is renormalized. But we know we are on the right track. And in the hypothetical scenario where we want to obtain a quantum version of this action, all possible counter terms will necessarily have the form of the ones that are already written here, because of the constraint and because we do not use the metrics. Okay? Well, in the torsion-free sector, we can actually recover all Einstein vacuum solutions, which is nice. And also, even though we start with a purely affine model, we only endow the manifold with an affine structure. We can still have 2 metric tensors coming from the symmetric and the antisymmetric part. So the Ricci tensor comes from the symmetric part of the affine connection, and this P tensor, which is called the Poplawski metric tensor, comes from the product of 2 torsion tensors, which is the antisymmetric part of the affine connection. Okay? And interestingly, we can actually couple a scalar field in this model without the use of a metric tensor. And we can use this scalar field to generate inflation in our model. Okay, so we have the action, we have some nice features, and right now what we need to do is to vary the action to obtain the field equations. And we have 3 irreducible fields. So if we vary the action with respect to the gamma field, which is the symmetric part of the connection, these are the field equations. And this is just a picture, I didn't write this. And if we vary the action with respect to the B field, these are the field equations. Fun story, I actually varied the action by hand because I didn't know how to use any software. So this took me a while. And these are the field equations for the I field. Okay, so we have the action, we have the field equations, and we want to do cosmology. So we need to build an answer for the affine connection that is compatible with the symmetries of the cosmological principle, which are isotropy and homogeneity. And how do we do that? Well, we use the Lie derivative, and we compute the Lie derivative along the Killing vectors that generate the symmetries of isotropy and homogeneity, which are translation and rotations. And this is the expression for the Lie derivative of the symmetric part of the affine connection. And if you notice, there is an extra term right here. That is because the connection is not a tensor. Okay, so it doesn't transform as a tensor, and it has this non-homogeneous term. Okay, so we compute the Lie derivative, and to find the answer that is written right here, we need to solve like 64 differential equations, but this is the final form of the answer. And what we found is that the symmetric part of the connection, it is defined by only 3 time-dependent functions. However, the first coefficient is in red, and that is because under a time reparameterization, we can actually vanish the first term, and we can repeat the same idea for the B field and the A field. And the final structure of the cosmological answer, it is written right here. So the symmetric part of the affine connection only depends on two time-dependent functions. The B field, which is related to the torsion tensor, only depends on one time-dependent function, and the A field only depends on one time-dependent function. Okay, so we have the answer, we have the field equation. What we do now is that we plug the answer into the field equation, and what we get is this. So this is these are the dynamical equations for the polynomial affine gravity in the frame of cosmology, and these are 5 differential equations for 4 unknown functions of time, and we need to solve this. And actually, we can solve this, and we can find an exact solution to this problem. And to see this, well, I don't know if you can see this, but the first equation has a structure of something times c equal to 0, and the second equation has a similar structure, another something times g equal to 0. So that tells us right away that we have 4 different branches, and we can study every branch, and we can solve this and find an exact solution. And the exact solutions are right here. So h is like something 1 over t, g is something like a power law solution, c also like a power law solution, and the last one, vanish. And alpha, beta, and gamma are related to the coupling constant. Okay, so we have the solution. What can we do with this? Well, we have an idea. In standard cosmology, we have 2 fundamental fields. We have the metric tensor, and we also have the energy momentum tensor. Okay, whereas here we have the Ricci tensor, we have the Poplawski tensor. So we can play this like a similar idea between those type of gravity formulations, and the C function that defines the torsion could play an analog role to the energy density, and the Ricci tensor allow us to define a affine scale factor. So what we do is that we can fix the parameters alpha, beta, and gamma to find the explicit, well, it's not explicit, but to find well-known solutions in general relativity in this context of polynomial affine gravity. So we can actually emulate radiation era, non-relativistic matter era, and we can find constraint to have an accelerated expansion. So to finish this presentation, I just want to highlight that we use the torsion tensor to emulate an energy momentum tensor, and the torsion tensor acts like a source of matter in this type of affine gravity. Okay, and that's it. Thank you for your time. Question time.
Just is a curiosity. Did you try also not doing only cosmology, but other kind of tests? It's interesting, no? The idea to let's say mimic something.
Yeah, like emulate something. Yes. Well, at the moment we are currently working with spherical symmetries, but we want to start with something much easier. And in cosmology, we have 6 scaling vectors. So we have a lot more constraints on the answer that if we want to do some spherical symmetry, which only has 3 scaling vectors. But we are working right now. Yeah.
Hi, and thanks for your nice talk. I wanted a short question. Could it be like imposing the Lie derivative of the connection equals to 0 be incompatible somehow with some of the connection equations?
Connection equations?
Yeah, because you show like a lot of equations of motion for the connection, and then you impose like the Lie derivative of the connection equals to 0 for some symmetry. Could it be possible that this is incompatible with some?
Well, I think at least when I derived the explicit form of the Lie derivative of the connection, what I did is that, well, basically I compared 2 vectors living in different tangent space and move one from one point to the other by a coordinate transformation, and that induced the non-homogeneous term. But in that process, I never used the metric tensor.
Okay. Yeah.
So I think.
So there's a question online.
But I think it's okay.
Okay, nice. Because in our deliberate approaches, there is also people imposing like the Lie derivative of the connection equals to 0. It's just the connection has much more restrictions in our models. But at some point it happened that someone found them.
But with the same symmetries?
With metric. I mean with metric and connection, and then they impose the Lie derivative on both terms.
Right.
And then there was some sort of problem there.
Okay, but what I can't do is upper and lower the index line. Yeah, that's something I cannot.
Yeah, I know.
It's not allowing this.
Yeah, I know. Because I don't know.
Yeah.
Well, I am very grateful for the possibility to participate and to make a question. So my question will be the following. In principle, we know that all gravity theories have some difficulties. Normalizability, many theories are non-normalizable, ghosts, etc. What are the difficulties of the affine gravity in comparison with the Einstein gravity? What are the problems which, by your opinion, have faults, have problems within the affine gravity?
Okay. At the moment, we haven't studied yet if there are ghosts presented in this theory. And actually, we haven't done yet the perturbation model because in standard general relativity, one perturb the metric tensor. And here you have to perturb the affine connection, we have another index. So it's not something quite trivial or straightforward to do that, but that is something that we are going to do. That's why I'm here.
So, I think it's finished. So, we move on. Thank you again, our speaker.
Yeah.